In last class, we are looking into modified Gram-Schmidt algorithm. The idea of Gram-Schmidt algorithm is to consider have a set of linearly independent vectors and then form a mutually orthonormal set of vectors out of that. This is done in a way you the first vector you consider the vector itself and then divide it by its length and get a normal vector or a unit vector on that direction. For the second vector onwards, you take a vector, project that vector along the already settled orthogonal vectors and subtract these components from that particular vector, and whatever will be remaining with you is perpendicular to the already settled set of orthogonal vectors, and this vector, take this vector, divide it by its length, you will get another unit vector. Now, you get a set of orthonormal vectors up to this vector and move forward. So, what we have seen is that as we take one particular vector v 1, for example, we take one particular vector v 1 v I, and we have a vector, we have few orthogonal vectors q 1, q 2, q 1, q 2, q 3, so on. So, we project v I on q 1 and this is say projection of v I on q 1, this is projection of v I on q 2, this is projection of v I on q 3. We subtract all these things from v I and get a new vector which is u I, and then q I, the next orthogonal vector is u I by mod of u I. However, when we subtract all these projections, so when we first take v I and subtract its projection from q I, whatever we will get will be v I minus projection of v I on q I. This is perpendicular to, or rather q 1, this is perpendicular to q 1. Then we subtract from this vector which is already perpendicular to q 1, we subtract projection of q I v I, this is, from this we again subtract projection of q 2 of u I on q 2. This will be perpendicular to q 2, this is also perpendicular to q 1. However, if we have number of vectors, and why this is both perpendicular to q 1 and q 2, because whatever is perpendicular to q 1 has no component in q 1. So, from this whatever we subtract will still remain perpendicular to q 1. However, in a numerical implementation what happens, when we do this for number of vectors, it becomes perpendicular to q 2, but does not remain perpendicular to q 1 due to round of errors. So, the solution becomes that, which is the modified Gram-Schmidt algorithm, that instead of projecting v I every time and subtracting these projections from v I, what you do, you make this as u I 1, which is projection of v I minus projection of v I on q 1. Then the next step in modified Gram-Schmidt method will be u I minus projection of u I on q 2. These two steps are similar, however, exactly same arithmetically we can see. However, as this is as we are not subtracting anything from this projection, which is v I minus projection of v I of q 1, we are taking u I and projecting u I on q 2 and subtracting this from u I, the round of error we are making in this stage is again projected on q 2 and being subtracted. So, round of errors are in a sense be getting cancelled, and this always remains perpendicular to q 1 and q 2, and this is the idea of modified Gram-Schmidt method. And we have a modified Gram-Schmidt algorithm where the dot product we take not with the initial set of vector, rather the initial vector we subtract its from the initial vector we subtract its projection along one particular q, and then we take the modified vector for the dot product. And now, if we see the an example that we are considering a set of linearly independent vectors in R4, and we are taking 3 vectors, 1 epsilon 0 0, 1 0 epsilon 0, 1 0 0 epsilon. Epsilon is a small number, and 1 plus epsilon square, epsilon is very small, say for example, epsilon is 10 to the power minus 6. So, epsilon square is 10 to the power minus 12 is further small, and we make the approximation 1 plus epsilon square is the 1. So, this approximation actually mimics round of error, because for epsilon is equal to say 10 to the power minus 6, 1 plus epsilon square, which is 1.10 to the power minus 12, right. So, 0 0 0 0 0 0 0 0 0 0 0 1. This we are doing a round of error, and we are considering this to be 1. So, though this is not any computer implementation, however, we are solving a problem in pen and paper, but we are doing a substitution of round of error here. So, when in this case when we apply Gram-Schmidt classical Gram-Schmidt technique, we get the following orthonormal set of vectors. Q1 is 1 epsilon 0 0. So, this has again a length 1, that is the orthonormal that is the approximation doing here. Its length is root over 1 plus epsilon square, and we are considering it to be 1. 1 minus 1 0 minus 1 0 0 minus 1 0 1 by root 2 by root 2. Okay, these are orthogonal set of vectors, and these are obtained after doing the mimicked round of error. Now, if we look into the modified Gram-Schmidt orthogonal vectors, they are not same as this, because at certain step there is 1 epsilon square which appeared in Gram-Schmidt method, which did not appear in modified Gram-Schmidt method. So, you do not have to neglect that epsilon square this thing. This, however, if we write epsilon square in both the if we have not disregarded that epsilon square which is coming in classical Gram-Schmidt method, we would have got the same set of vectors in both cases. But as epsilon square is very small, like a computer approximation, we are doing 1 plus epsilon square is equal to 1. This ideally should give right result, and if we think of writing a computer program, we have to deal with systems where this type of situations will occur, where there will be numbers which are which are not the exact numbers, rather the numbers which are replaced by a truncated version of these numbers, where the round of error is already there. Okay. So, we see the modified Gram-Schmidt solution. The first one is 1 epsilon 0 0, second one is same 0 minus 1 1 0 by root 2, the third one is changed 0 minus 1 minus 1 2 by root 6. The third vector in Gram-Schmidt and modified Gram-Schmidt are different, and that is because of this approximation 1 plus epsilon square is equal to 1 is made somewhere here, which has not been made in modified Gram-Schmidt at that particular location, and you can try it yourself, you will see that this step is arising. So, this is the solution is actually very straightforward. So, these are the different value of Q3 we are getting in Gram-Schmidt and modified Gram-Schmidt method. And now, if we check orthogonality, the classical Gram-Schmidt Q2 transpose Q3 is not giving me 0, rather giving me a half. However, the modified Gram-Schmidt is giving me the right result, because this epsilon square approximation is avoided in modified Gram-Schmidt, which is not avoided in classical Gram-Schmidt method. And once you do it, practice this problem yourself, you will be able to identify that particular step where this has been done. So, modified Gram-Schmidt obviously gives us a much stable solution. This error will only come when there is some epsilon square which is which neglecting which can hinder the problem. Ideally it should not be, because this is a small value, but this is changing the solution. So, we call this to be a numerically unstable method, because it might give good result, classical Gram-Schmidt might give good result in certain cases, but there are small changes in the vectors and it can give entirely different result, and the results will be wrong. In a sense, the vectors are not mutually perpendicular to each other. However, modified Gram-Schmidt is a stable algorithm and it should give you right result in all the cases. So, now we will know that if we have a set of independent vectors, we can get a set of orthonormal vectors using those independent vectors. How we can use it for the purpose of matrix solvers? So, what we will do, we will consider a matrix with independent columns. And what is the importance of having a matrix with independent columns? It can be very easily shown. You can take it like a small exercise yourself, that if the matrix has independent columns and we solve Ax is equal to b, x will have at most one solution. Infinite solutions are not possible. Maximum there will be one solution if matrix A has independent columns. If the columns are equal to the number of rows, then there will be exactly one solution. If the columns are less than the number of rows, so that you have less variables, but more equations. Columns are less than number of rows. However, if the columns are independent, you will still get one solution, and that is why in case of singular matrices, when finding the particular solution, we remove the dependent columns from that, so that we have a independent we only have independent columns in the equation. So, what we will try to see is that we will form a matrix with independent columns and do a Gram-Schmidt orthogonalization over that matrix. So, that matrix will be transformed to a Q matrix or to a matrix with orthonormal columns. If it is a square matrix, it will be a square Q matrix, which is called an orthogonal matrix. However, so we will get a matrix with orthonormal columns. Now, solution is very easy, because with a orthonormal basis, we have earlier seen that we can take the right hand side vector and project it on orthonormal basis. Projection with each of the bases will give me each component of the solution vector. So, solution will be much simpler. So, and there is a more formal way of proposing the solution here. So, what we will do, we will start with the equation Ax is equal to b, and now take A and do a Gram-Schmidt orthogonalization on A, and see how the equation looks like and what are the ease in solving the equation. So, this is called a QR factorization. Start with a matrix A with independent columns V1, Vj, Vk, and let us run Gram-Schmidt orthogonalization steps on each of the vectors to get a orthonormal set of vectors. So, I have I will have the first vector V1. It is very easily it can be orthonormalized, like we will only take the length of that first vector and divide it by that, and we will get the vector q1. And the relationship between v1 and q1 is q1 is independent unit vector. So, v1 q1 dot v1 is basically length of v1, a vector with unit vector dot product. If they are on the same direction, it is the length of v1 along q1. For v2, v2 is constituted, or sorry, q2 is rather q2 is constituted as take v2, project it along q1, subtract that part from it, you will get the part which is perpendicular to q2, perpendicular to take v2, project it on q1, subtract that projection from v2. So, you will get a component which is perpendicular to v2 and get q2 out of it. So, v2 can be decomposed in these two orthogonal vectors q1 and q2. Similarly, for q3, how do we get q3? We took v3, projected it on q1 and q2, subtracted these projections from v3. What is remaining with us? v3 minus the projections, normalized it, got q3. So, V3 is again composed of 3 vectors or can be decomposed into 3 orthogonal directions q1, q2, q3. Similarly, we move ahead V4, there will be 4 vectors in which V4 can be decomposed q1, q2, q3, q4, and Vk, kth vector will be decomposed in all k independent orthonormal vectors. So, if a vector is like V1, there is only one basis vector which express V1. For V2, there is only one basis, there are two basis vectors q1 and q2 which gives you V2. For any vector B on an orthonormal basis q1 to qn, it can be expressed as q1 transpose B q1, which is projection of B along q1 on that direction, projection of B along q2 on that direction, and similarly projection of B along qn and on that direction. So, we can write V1 is q1 transpose V1 q1, V2 is q1 because it is only it has q1 and q2 components into q2 and so on. So, we get a triangular form of equations here. The equation set gives us a nice triangular form. Remember, V1, V2 to Vk are columns of a matrix A, and we are thinking of solving x is equal to b. So, if we put this the right hand side as the column of matrix A, if we just substitute it, what happens then? So, V1, V2 up to Vk and Q1, Q2, Q3 up to Qk are column vector. The matrix A and Q, this is column of these vectors are this is columns of A, and this is columns of Q. Q is the vector with orthonormal columns. So, the matrices A and Q are related as these columns V1, V2 up to Vn is equal to the columns Q1, Q2, Q3, because if I go back, V1 is Q1 transpose V Q1, V2 is Q1 transpose V2 Q1 plus Q2 transpose V2 Q1. So, the column V2 is something into column Q1 plus something into column Q2. So, in that sense, if we go, we can write that the matrix A, this is the matrix A, this is the matrix Q multiplied by a triangular matrix. So, V1 is Q1 into Q1 transpose V1, V2 is Q2, these are the column vectors, this is not a single entry, this is rather a column, a vector. The vector Q2 V2 is equal to Q1 transpose V2 into Q1 plus Q2 transpose V2 into Q2 is combination of these two columns, so on. So, we get a equation where we write A is equal to Q into R, where Q is an orthonormal matrix and R is a triangular matrix, or R is rather better to write a lower triangular matrix. And we get if A is m into n, that means A has m rows and n columns. So, there are n independent columns and each are in, all the column vectors are members of vector space R m. So, A is m into n, Q is m into n and R is n into n. So, if we have n independent columns in R m, that means either columns are equal to rows or columns are less than number of rows. So, A will have a shape like this. A is m into n. M is greater than equal to n because there are n independent columns. So, m can be at most m. This equal to Q, Q is also M into N, a rectangular matrix, into R, which is N into N, which is a square matrix, a small square matrix. So, this is a lower triangular matrix, and a triangular matrix must also be a square matrix. So, A is a rectangular matrix that is obtained as another rectangular matrix Q into square matrix, square lower triangular matrix R. Now, if I substitute this into the equation A x is equal to B, because one idea is that if we have orthonormal columns, it is easy to solve the equations. You only have to, like, we have q x is equal to c, you only have to take c and project it along each columns q1, q2, q3. So, c dot q1 will give you x1, c dot q2 will give you x2, so on. So, solution becomes only a projection operation. And now, we saw that how from A is any general rectangular matrix, we have to convert it into a transform A to a Q matrix, and that is doable as A is equal to Q into R, where R is the lower triangular square matrix, R is a lower triangular matrix. So, if we write A x is equal to B as Q R x is equal to B, and see how to solve this equation, and we will also see whether we can take advantage of that Q is orthonormal, and so finding solutions are easy. So, A x is equal to B on a Q R factorization on that will give us Q R x is equal to B, which can be represented as a system of two equations. First is Q c is equal to B with R x is equal to C. Now, Q has, so there are two things, this Q is orthonormal and R is lower triangular. So, the first equation Q c is equal to B can be solved as projecting B on Q. What is known to us? B is already known to us from the matrix A. You run a Gram-Schmidt process and get the orthonormal matrix Q. So, this can be obtained using say a modified Gram-Schmidt algorithm. Gram-Schmidt process on A. So, take a matrix A, run modified Gram-Schmidt on A, you will get the Q matrix, and in these steps you can find out what is the R matrix. Now, Q is an orthonormal matrix. So, Q c is equal to B can be solved as just projecting C on Q. So, we can write C1 is equal to Q1 transpose B, C2 is equal to Q2 transpose B, and so on. And then we have the equation R x is equal to C, which is the lower triangular system. So, you can find out C from them. The last equation, or if I look into R, so, this is a lower triangular matrix. That means the first equation, so R has a shape like this. R11, R12, R21, R21, R22, R31, R32, R33, and here we have x1, x2. This is equal to C1, C2. So, I can directly find out x1 is equal to C1 by R1, then x2 is equal to C2 minus x1 R21 divided by R22, and so on. So, the second equation R x is equal to C can be directly solved as R is a lower triangular matrix. So, x is equal to B equation for any rectangular or for a square matrix also becomes easily solvable, or other than Gauss elimination, Gauss Jordan, or the third one we discussed about LU decomposition or TDM. TDM is restricted only for tridiagonal matrix, but general purpose we have seen Gauss Jordan, Gauss elimination, and LU decomposition. Other than these methods, we can also use a keyword decomposition method in which we can solve a equation system, and the efforts are not that involved like Gauss elimination. Efforts are probably simpler than Gauss elimination. We are not actually counting the number of steps, but this can be an exercise that count the number of steps involved in a keyword factorization. However, if we have, or in some way we already have the keyword factorization of a matrix, we can solve the equation very quickly. In a sense, Rx is equal to C is directly solvable. If there are n equations in n steps, we can solve that in order of n steps, and then Qx is equal to Qc is equal to B is also solvable. We only have to project B along each of the Q1 and the solutions will be there. But again, like LU decomposition, the solution is simple when you have LU decomposition already, but LU decomposition itself is a costly process. Similarly, QR decomposition, the solution is simple if we have already have the QR decomposed form, but getting keyword decomposition needs a Gram-Schmidt process, which is relatively costly process. Okay. So, the further important thing happens if we if we think of QR factorization of normal equation. A normal equation is, instead of Ax is equal to B is not solvable, the columns are independent, but the columns do not span the entire Rn, entire Rm, that columns do not span entire Rm. Therefore, X is equal to B does not have any solution. So, X is equal to B is not solvable. So, what do we do now? Then we try to find out the best estimate of X. We get the normal equation A transpose X, X is the best estimate is equal to B. A QR estimate, this is not actually, we use a X tilde here. So, X tilde is best estimate of X is equal to B with least square error. So, also from a least square method we can get this system of equation, and we have A transpose A x tilde is equal to A transpose B. So, for the equation, this is not A B, I am sorry, this will be A transpose B, A transpose B. So, we have the equation A transpose A x tilde is equal to A transpose B, and now we put the keyword decomposition here. So, which is keyword transpose Q R x tilde is equal to keyword transpose B, and transpose of product is product of the transposers in the different order. So, this is R transpose Q R x, and now what we know is Q transpose Q is an identity matrix. So, we get R transpose R x tilde is equal to R transpose Q transpose B, cancel R transpose from both the sides. So, we have R x tilde is equal to Q transpose B, and we again end up with a lower triangular matrix, but now the solution, now we do not have to do any projection to, or we do not need to solve Q C is equal to B. We only have one equation which is of lower triangular form, R x tilde is equal to Q transpose B, and this equation is directly solvable as R is lower triangular form. So, QR factorization actually is much useful if we have the normal equation. We will later see that many very sophisticated solution techniques are not that efficient for normal equation, because this A transpose A matrix is a complicated matrix to deal with when solved. However, if we have a keyword decomposition, the A transpose A matrix, we do not have to deal with that, rather we deal with R x tilde is equal to Q transpose B, and very easily we can solve this equation. This is like in steps we can solve this equation, because R is a lower triangular matrix system. So, this is one of the largest utility of keyword decomposition when you are trying to solve normal equation A transpose X tilde is equal to A transpose B. So, we with this lecture we finish most of the direct solvers we plan to discuss here, and we go through the set of direct solvers which we have gone through the set of direct solvers yet, which are Gauss elimination, then LU decomposition, Gauss Jordan, and TDMA or tridiagonal matrix algorithm. We have seen it for one specific purpose when the matrix is tridiagonalized, and we have discussed about a variant of tridiagonal matrix algorithm which is not a direct solver, which is actually an iterative solver. However, that TDMA can be used when the matrix is not tridiagonal, rather pentadiagonal or septadiagonal form. And we have now looked into another matrix solution technique, which is keyword decomposition. So, next part of this course we will discuss with iterative solvers, but before going into iterative solvers we will have a brief review of eigenvalues and eigenvectors of matrices, which we will do in next few classes, because they are important in iterative solvers. Also they will help us to understand the behavior of iterative solvers from the understanding we have already developed on X is equal to B systems using direct solvers. So, next class we will start discussing on eigenvectors and eigenvalues. Thank you.